So this is the second lecture on sinusoidal steady state analysis. What we'll do in this lecture is I'll go through different examples to illustrate different techniques and revise some of the techniques we had studied earlier for DC circuits. First thing, before doing the examples, I wanted to define what are phasors. So as we saw in the last lecture, in sinusoidal steady state, all currents and voltages will have this general form xm cos omega t plus phi, assuming that all the independent sources have a frequency of omega and the circuit is linear. All those are assumed. And to analyze these circuits, we will first convert this circuit to the complex or the frequency domain, which we did last time. So we'll say xm cos omega t plus phi will become xm e raised to j omega t plus phi, and the e raised to j omega t will cancel out in all the differential equations. So we will be left with xm e raised to j phi for each current and voltage in the circuit. This quantity xm e raised to j phi, which is of course a complex number, is called a phasor. So this is a terminology used in electric circuit analysis. So a phasor has of course a magnitude and a phase, or it could be represented as some a plus jb in a rectangular coordinates. This is polar coordinates. So this is similar to a vector which also has a magnitude and a phase. So the word phasor comes from the word vector, except that these are not vectors. These are magnitudes and phases of sinusoidal functions. It is of course a complex number. It has no dependence on time. So I had mentioned this last time. Once we convert the circuit to frequency domain or the complex domain, time disappears from the circuit. This is important because one should never draw a circuit in the frequency domain that has time in it. Cos omega t should not appear in the complex domain circuit. Okay, for convenience, this xm e raised to j phi is often written as xm angle phi. This is just a terminology. It is easier to write angle phi than e raised to j phi. This basically means this. All right. And when one does this, or well, this also, generally the convention is phi is written in degrees because it is easier to visualize degrees than radians. All right, theoretically, well, I mean, you could do either, but the convention is to write it in degrees. All right, so with this, we solve a bunch of different example circuits. So here is our first circuit. So we have basically a parallel RLC and a current source. The values of the current source and RCL are given here in the time domain, and we are asked to find the voltage V and the inductor current IL. So the first thing we do is convert the circuit to frequency domain. So 2 cos 10 raised to 4t becomes 2 angle 0 because the phi in this is 0, so which is just 2. So we'll call this IS. And in amperes, of course. The frequency is 10 raised to 4. So R will stay as R. C is given to be 50 nanofarad. So that will become 1 over J omega C. So 10 raised to 4, 50 nanofarads, which turns out to be minus J 2000. And the dimension of 1 over omega C is ohms. L is given to be 400 microhenries, so that is becomes J omega L, which is J4 ohms. So as you may have seen these circuits before, inductors have a plus J and capacitors have a minus J, because capacitor is 1 over J something and 1 over J of course is minus J. Right, and these are called impedances. So minus J 2000 and minus J4 are called impedances. Alright, so the next thing we do is we draw the circuit again. The circuit stays the same, the values become complex numbers. So we have 10 ohms minus J2000 and plus J4. And now we analyze this circuit using all our circuit principles. So we want to find this voltage. So we say, well, there is a current and then there are three impedances in parallel with each other. If we call them Z1, Z2, Z3, then the Z equivalent of these, it will be 1 over Z equivalent equal to 1 by R plus 1 by Z1 plus 1 by Z2 plus 1 by Z3. And so we can solve this and so it turns out to be J2000 by 499 plus J200. So that is the equivalent impedance of all these three connected across the current source. So then the voltage will simply be this current multiplied by Z equivalent. So we get V equal to the Z equivalent into 2. The current source was 2. So that gives us J4000 by all this. And the inductor current we were asked to find is the voltage. So let's go back. Voltage divided by this impedance, which is J omega L or J4. So V divided by Z3 is IL. So you get V divided by J omega L, which is V divided by J4. And that is 1000 by 499 plus J200. And V is this J4000 by 499 plus J200. Now, having found the answer, we want to convert this back to time domain. So to convert it back, we must write this as a magnitude and a phase. So this is basically a fraction of two rectangular numbers. We convert them to polar. So as I said last time, each of your calculators will do this. You'll have to figure out how to convert rectangular to polar. The numerator, of course, you don't need to use a calculator. This has only an imaginary part. So this is 4000 and the angle is 90 degrees because J corresponds to a 90-degree angle. So 4000 angle 90 degrees. The denominator will turn out to be 537 angle 21 degrees. Then we divide the magnitudes and subtract the phases. So 4000 by 537 is 3.8. 90 minus 21 is 69 degrees. So the voltage in polar coordinates is 3.8 volts, angle 69 degrees. So we convert it back to time domain as 3.8 cos 10 raised to 4t plus 69 degrees. And similarly, you can find IL. I have not shown the calculation, but IL will turn out to be, so when you do this, it will turn out to be 1.36 cos 10 raised to 40 minus 21 degrees. So again, one quick check when the circuit is this simple is, so if we go back, the voltage V and the current IL are the voltage and current for the inductor. And for the inductor, the current will lag the voltage by 90 degrees as we had seen last time. So the phase difference between the V and the IL has to be 90 degrees. As we can see, 69 plus 69 minus 21. So the difference is 69 minus 21, which is 90 degrees, as it should be. So it's a quick check in case the circuit is simple. All right, let's do the next example. So this is, okay, this is also a simple example. So a voltage source is given to be 5 cos omega t plus 45 degrees. Omega is 10 raised to 5, 200 micro, 20 nano, 500 micro. All right, so we call these as, so we convert each of these to complex domain. So 200 micro times 10 raised to 5, so that gives J20. 500 micro gives J50. 20 nano will be 1 over 10 raised to 5 into 20 nano, which gives minus J500 ohms. So I'm calling them Z1, Z3, Z2. I forget why I've called this Z3 and it doesn't matter anyway. So Z1, Z2, Z3. Alright, so Z1, Z2, Z3. And we are asked to find V1, this voltage V1. So what we'll do is we'll say as well Z2, Z3 are in parallel. So we combine them. So Z3, 2 parallel Z3. And then V1 we find by voltage division. So this impedance divided by this impedance plus this into Vs. So I'm just illustrating these simple techniques we've studied before in the complex domain. So is a Z23, Z2 parallel Z3, and then V1 is equal to Z23 by Z1 plus Z23 into Vs. And then we find all these quantities. So Z2 parallel Z3 is minus J500 parallel J50, which if you do turns out to be J500 by 9. And V1 is Z23 by Z1 plus Z23. So this J500 by 9 divided by J20, which is Z1 plus J500 by 9 into Vs. Vs is 5 angle 45 degrees. Alright, so we saw, so you convert this to polar and then divide the magnitudes, do all the phases, there will be 3 phases, and add or subtract, and finally we'll get. So incidentally this J cancels actually here, right? The J cancels. So this is only a real number. There is no phase here, and so the real number is 3.68. So we get V1 equal to 3.68 cos 10 raised to 5t plus 45 degrees, which interestingly has the same phase as the voltage, the source voltage. The source voltage and this voltage have the same phase. There is no phase change. Why is that? The reason this happens is because all our impedances, all our elements are either capacitors or inductors. Alright, and so all capacitors, inductors all have a J here. There is no resistor, and so if there are only J elements in the circuit, then as we see here, when we find any other voltage in the circuit, because all circuit elements have a J, voltage division, parallel, series, everything, the J will stay as J, and eventually the J will cancel out. So, and so any voltage will be some real number times the source voltage. And so the real number of course will not change the phase of the original source voltage. So if there are only, so these are called as reactive elements, right? Inductor and capacitor. So if the circuit has only reactive elements, then the phase of all the voltages in the circuit will be the same. The current will have opposite, not opposite. So the current in the capacitor will lead the voltage by 90 degrees. The current in the inductor will lag the voltage by 90 degrees. So the current and currents across elements in elements will have a different phase, but the voltage will have the same phase. Okay, so let us look at a circuit with a dependent source. So here is a dependent voltage source of value 10I, where I is the current in the 10 ohm resistor. So we'll convert this first to the phasor domain. So the 1 Henry becomes j omega L equal to j10 ohms because the omega is 10, and the 0.5 Henry becomes j5 ohms, and the rest are all resistors. So here is the circuit, and the other thing we do is, so we have a 10 ohm in parallel with a j10 ohm. So we combine these two into one impedance, so that is 10 ohm in parallel with j10. So that's j100 divided by 10 plus j10. So that is j10 by 1 plus j. So these combine into 1 j10 by 1 plus j, and these two are in series, 5 ohm and the 0.5 Henry, which is j5. So 5 plus j5. So that becomes one impedance, 5 plus j5. So this becomes our circuit in the phasor domain or the complex domain. So this is a circuit. I'm doing nodal analysis, don't have to, you could do mesh also, it's up to you, but I have done nodal. So there are actually 3 nodes, 1, 2, 3, but this one node voltage is already known. There is a voltage source here, So we'll write a KCL for this super node. So we'll write one KCL only, and then one equation will come from the dependent source. So we'll write a KCL at this super node, which is here. So you say V minus 10 divided, V minus this 10 divided by 10 ohms is this current, plus V divided by this impedance Z1. And then we do a super node, so we'll do this current, so we'll say V1 divided by Z2 equal to 0. So this is a KCL for the super node that encloses this dependent source, right? And then Z1, Z2 we know, so that is one equation. It has two unknowns, V and V1. The other equation is for the dependent source, which is V1 minus V equal to 10I. So V1 minus V equal to 10I. I is this current. So this current is 10 minus V divided by 10 ohms. So this is 10 into I. So 10 into 10 minus V divided by 10 ohms. So the 10 cancels. So the numbers are conveniently very nice. So you get V1 minus V equal to 10 minus V. So V minus V actually cancels and we directly get V1 equal to 10 volts. And then V1 equal to 10 we substitute here. So we'll get an equation in V, which I have solved here. I'm not going through the solution. We'll just look at the final answer. So the final V is 10 into minus 1 plus J by 3 plus J. And then we convert this to polar. So incidentally, so this is minus 1 plus J. So the magnitude is square root of 2, which is 1.414. And the angle is tan inverse minus 1, right? 1 divided by minus 1 is minus 1. So tan inverse of minus 1 is 135 degrees. And then 3 plus J is all this. And then we divide the magnitudes and multiply by 10 and then subtract the phases. So V turns out to be 4.47 cos 10 t plus 116.6 degrees. All right. Let's do a very simple example of Thevenin's theorem. So we are given this network and we are asked to find the Thevenin's equivalent across A and B. So very simple. So there is a current, and in fact, you will often find in the textbook that sometimes, just to learn how to solve these circuits, the circuit itself has been given in the complex domain and you are asked to find the answer in the complex domain. So this is the case. So there's only one current. The current flows in this loop. No current flows here because this A to B is open circuited. So the voltage VAB is actually equal to the voltage across these two because there is no voltage across this impedance. And this voltage is equal to this current times this impedance. So it is 2 into 1 plus J. So that is the Thevenin's equivalent voltage, 2 plus J2 volts. The Thevenin's impedance, the impedance looking into A and B, to find it we'll remove the current source, open circuit the current source. So what we are left with is these two in series. So that is just 1 plus J minus J. So that is just 1 ohm. Alright, so the Thevenin's network is VAB 2 plus J 2 volts in series with 1 ohm. Alright, let's look at this circuit. Again, I don't know what you've seen and not seen, but this is a resonant circuit. We'll look at this in more detail in the next week lectures, I think. But let's just analyze this for one particular set of values. So 4 ohms, 80 micro, 2 nanofarads. The source is 2 cos omega t and omega is given to be 2.5 mega radians per second. So we convert the impedances. So 80 micro becomes J200, 2 nano becomes minus J200, and the voltage source is simply 2. Oops, sorry. So we write this circuit. So 2 volts, 4 ohms, J200 ohms minus J200 ohms. And so the current, I think what is the question? find all three voltages. Okay, so we find the current and then we find each of the voltages. There's only one current, so the current is the voltage 2 volts divided by the sum of the three impedances. So 4 plus J200 minus J200. So the J200 and minus J200 cancel, so we get a current of 2 by 4, which is 0.5 amperes. So this, as you perhaps know, is the characteristic of a resonant circuit when the resonance, the simplest resonance circuit is basically an RLC circuit, either series or parallel, there are both types. And if the inductive impedance has the same magnitude as the capacitive impedance, J200, then the sum of these two will become 0. And that is the characteristic of a resonant circuit, where the inductive impedance and the capacitive impedance cancel each other. So the net impedance of the circuit is purely resistive. That is a resonant circuit. Alright, so let's just find the voltages. So we found the current, then the voltage is the current multiplied by the individual impedances. So 4 times 0.5, so 2 volts. The inductive is 4, I'm sorry, what is 4? Yeah, 4 is resistance times 0.5. Okay, that's okay. The inductor voltage is J200 times 0.5, which is J100 volts, and the capacitor is the negative of that. So what we find here is that the source voltage that is applied is 2 volts, but the voltages across the inductor and the capacitor have a magnitude that is 50 times the source voltage. Alright, so this is again a characteristic of resonant circuits, good quality resonant circuits. The good quality is that the resistance has to be small. As I said, we'll discuss this more detail next week. And these circuits are used as receivers in a large number of communication receivers. So when you have a signal coming in the air and you want to catch it and convert it to an electrical signal and then process it. So this 2 volt could represent the equivalent of the voltage that is being caught from the air, and this is the circuit that produces an output either across the capacitor or the inductor, which is 50 times the voltage that was caught. As you can imagine, the voltage that is caught in the air will have an extremely small magnitude, because let's say you have so this applies to mobile phones, everything, radios, everything that travels in the air. So you have a mobile tower and it is sending a signal all over. The signal is sent throughout space. For the conversation, let's say you are having on your phone. So the mobile tower doesn't know where your phone is, except that it is in the vicinity. So it is sending a signal out in all 3 dimensions. So by the time the signal reaches the mobile phone, the strength of the signal is extremely small, microvolts or nanovolts, like that. So that has to be caught. The other thing that has to be done is there are of course a zillion signals floating around in the air of different frequencies, and so the mobile has to distinguish between the signal it wants, the signal on the frequency you are talking to, from all the other frequency signals. So this resonance circuit gives a 50 volt output at that particular frequency. At 2.5 megaradians is the frequency at which the inductor and capacitor impedances are equal. At no other frequency are they equal. So the signal that you are talking at has a particular frequency, and the resonance circuit in your mobile phone is tuned to that same frequency, and so it will catch or give an output. So this circuit will give an output 50 times of what is applied to it only for that specific frequency, At all other frequencies, it will give a much smaller voltage. And so this is how the fundamental receiver, communication receiver functions. We'll look again, as I said, we'll look at this more detail next week. All right. What was this? Okay. So again, this is a different representation. So the resistor voltage is 2 cos omega t. The inductor voltage is 100 cos omega t volts. The capacitor voltage is 100 cos omega t minus 90 degree volts. And then this is just a kind of vectorial representation of these signals. So of the phasors actually. So the resistance voltage is in phase with the source voltage, and those both are 0 degrees and they are small in magnitude. The inductor voltage leads the resistance voltage, the capacitor voltage lags the resistor voltage, and they are 50 times the resistor voltage. Of course, this may not be to scale, right? But that's okay. All right, one more circuit. So this is an op-amp circuit. This is called a filter. Again, we'll see filters more next week, but this is just one. We're just analyzing this circuit. So the question is, find VO. Vs is given to be 0.1 cos omega t. R1, R2 and C are given. And we are asked to find VOT for 3 different values of the frequency omega. Alright, so what we'll do is we'll find an expression for VO in terms of omega and then substitute omega values to get the actual expression for VO. So first we analyze this circuit. So we say, well, of course, V minus is equal to V plus for the op-amp. And then we write a KCL at the negative node. So we'll say, this node is 0. So as we do for op-amps, we'll do the sum of the currents entering the node to be 0. So we'll say Vs by R1 plus VO by R2 plus VO by 1 over j omega c equal to 0. So Vs by R1, VO by R2 plus j omega c into VO equal to 0. We want to solve for VO. Vs is known. So we solve for VO. It's a very simple circuit. So the solution is VO equal to minus R2 by R1 into 1 by 1 plus j omega R2c into Vs. And we know R1, R2c. So we put values. So R2 by R1. R2 is 10 kilo ohms, R1 is 1 kilo ohm. So R2 by R1 is 10. So minus 10 divided by 1 plus omega into R2C. R2 is 10 kilo, C is 10 nano. So kilo nano is micro, 100 micro is 0.1 milli or 10 raised to minus 4. So you get minus 1 divided by 1 plus j omega 10 raised to minus 4 into Vs is given to be 0.1 volt. Alright, and now we substitute for omega the 1 kilo, 10 kilo and 1 mega and find the phasor for VO. We are actually currently interested in the magnitude. So what we find is that 1 kilo of omega, the VO magnitude is 0.94. So it's close to 1. So 10 times 0.1 is 1. So this is close to 1. When the frequency increases to 10 raised to 4, the magnitude drops to 0.7. When the frequency increases to 10 raised to 6, the magnitude drops to 0.01 volt. This, of course, qualitatively you can see the magnitude is of VO varies inversely as omega. As omega increases, the denominator magnitude increases, and so therefore the VO magnitude decreases. So this circuit is called a low pass filter because it is letting, so at the output, if the input frequency is low, 1 kilo radian or lower, then the output corresponding to that input has the same magnitude as the input. When the input frequency becomes larger, the output magnitude for that frequency is very small, 0.01. This is all close to 1. This is 100 times smaller. So this circuit does not let the high frequency signals to pass through. It kind of stops them from passing. That's why it's called a filter. It filters out the higher frequencies. It lets the low frequencies pass. So it's a low pass filter because it allows the lower frequencies to pass. So you can imagine a high pass filter where the circuit will allow the high frequencies to pass and not let the low frequencies to pass. All right. Okay, one last. So again, as I said, filters will do more next week. Okay, here is a very simple circuit. It has two sources. Vs is 5 cos 1000 t. Is is 2 cos 2000 t. The two different frequencies here. And L value and C value are given. And we have to find the voltage Vxt for this circuit. So how do we find? Now there are two frequencies, the L and C will have two different values corresponding to the two different frequencies. So which frequency to use now? So the only way to solve such circuits where there are two different frequencies present is to apply superposition. There is no other way of solving this circuit. Or you use a circuit simulator, right? Simulators will do what they'll do, but if I want to solve it on paper, either we have to do superposition or we have to write out the complete differential equation and solve the differential equation for the two forcing functions. Okay, so what we do is we use superposition. So we'll remove the current source, find Vx for only Vs applied. Then we'll short the Vs and find Vx for only Is applied. Alright, so we start with only the voltage source connected and in open circuit the current source here. So this is the circuit we get. And now because there is only one frequency in the circuit, we can convert the inductor and the capacitor to their equivalent reactances. So for the inductor we get J, 1000 is the frequency and 8 millihenries. So we get J8. For the capacitor, we get Z2 equal to 1 by J omega into 0.25 millifarads, which becomes minus J4. And then the voltage Vx, which we are supposed to find, we can find simply by voltage division. So Vx1 is equal to Z2 by Z1 plus Z2 into Vs. And Z2 is minus J4. Z1 is J8, so J8 minus J4 is J4, so you get a minus 5 volts. So Vx1 in time domain, converting this back, this is incidentally only a scalar, and so there is no phase here. So Vx1 is minus 5 cos 1000 t. Again, as we just saw a few minutes ago, the reason this is a scalar is both of these are reactive elements, and therefore any voltage in the circuit has the same phase as the source voltage. Alright, so now we do only the current source. So we short circuit the voltage source, and now we find the impedances again because the frequency is different. So omega is 2000, Is is 2 amperes. So we find the inductive impedance J into 2000 into 8 milli, which is J16. And then Z22, which is the capacitive impedance, is 1 over J 2000 into 0.25 milli, which is minus J2. And now the voltage Vx2 is Z12 parallel Z22 multiplied by the current Is. So we do Z12 parallel Z22 into Is. So J16 minus J2, J16 minus J2 into 2. We solve all this, then we'll get 4.6 angle minus 90 degrees. And so converting this back to the time domain, the voltage Vx2 is 4.6 cos 2000 t minus 90 degrees. Again, note that the current and the voltage are 90 degrees out of phase. The current has a zero phase here. So the voltage will be either plus 90 degrees or minus 90 degrees because all the impedances are reactive. Alright, so the final answer then for Vx of t is the sum, the superposition of the the voltage is due to the two different sources, minus 5 cos 1000t plus 4.6, I'm sorry, this is cos 2000t minus 90 degrees. All right, next lecture we'll discuss power in AC circuits.